Hey all, so we're going to talk about integrating with u-Substitution, which is your last big integration review. And then tomorrow you're not going to have a lecture. You are going to have 30 minutes of undivided practice with some integrating techniques from the back of the book. You still have a presentation problem, but just giving you that reminder, you shouldn't expect a lecture. And then after that, we'll move into chapter 6. So get yourself ready for notes, and we're going to get started talking about u-Substitution. Now, this method is specifically for things that what we see going on here where we're looking at products, meaning that we have one function times another. And what we're specifically looking for with u-Substitution is a product that looks like it might be a chain rule. So if you remember, the chain rule would be f prime of g of x times g prime of x. So you're looking for one of the factors on the outside to be the derivative of a factor on the inside. And then we'll use some of those skills from there. So in this case, let's look at number 1. We're looking at a product here, which means u-Substitution might be the right step. And we have a function here that has the derivative similar, but not exactly. And that's okay. It's okay if it's not exact. But we're going to say, oh, well, that's similar there. That's going to be our u then. That's how we decide which of these different pieces is going to be our u in our u-Substitution. Right, you're looking for that inner function for the most part. We'll look at a couple of cases that are a little bit different. So I will always start off by writing my function as u is equal to, in this case, x to the 4th plus 2. And then I'll take my derivative. So then du dx, and I am specifically writing in Leibniz notation as fractions, is equal to 4x to the 3rd. Now the reason I'm doing that is that if I look at my integral here, I have the cosine of x to the 4th plus 2, but I don't have 4x cubed. I have also an x cubed and then a dx. This is what I actually have that I'm going to substitute in terms of du. So this will be in terms of u. X to the 3rd dx, I will multiply up the denominator on both sides here. And then I want this because that's what I can actually substitute into my integral. So then I have du is equal to 4 times x to the 3rd dx. And I'm substituting x to the 3rd dx, so I want to divide away that 4. So 1/4 du is equal to x cubed dx. So now I'm ready to do my substitution, and I'm going to have my new integral is cosine of u times 1/4 du. And this is a much easier to integrate problem. I'm going to bring the constant multiplier out. This is the integral of cosine of u du. The variables match, which is how you can tell that we're ready to integrate. The integral of cosine is sine. So I have 1/4 sine of u. Don't forget your plus c. And now, since this isn't an evaluate problem, we're going to plug that right back in. And we have 1/4 sine u is x to the 4th plus 2 plus c as our final answer here. Now, this is not the only type of problem that we'd use u-Substitution with. It's the traditional one. Sometimes u-Substitution can be really helpful for one that we don't necessarily immediately know the antiderivative of. So we ask ourselves, can we turn it potentially into a chain rule product type problem? So in this case, we have tangent theta d theta, and this is a classic u-Substitution problem, and I'm going to rewrite this as the integral of sine theta over cosine of theta d theta. And in order to write this as a product, I would divide out the the fraction, and we end up with 1 over cosine of theta, which we might even just write as cosine of theta to the -1, so that it looks like a chain rule. It's a function inside of a function, times sine of theta d theta. And the reason we choose cosine to write like this is that then we have the chain rule, versus if we split it up, then we have d theta over cosine, which is not the same product that we would be expecting. Now what we can say is, oh, well, we have a function here, u, and its derivative sine. Again, it's not perfectly lined up, so we're going to have to write du d theta is equal to negative sine theta. We have just positive, so we can switch around our negatives, multiply the d theta over, divide by the negative, and we end up with du by itself is equal to sine theta d theta with a negative on the other side now. So that's what we're actually going to substitute with. And when we integrate, we will end up with the integral of u to the negative first du with a negative as the coefficient. Now, one thing you've noticed is I haven't added the bounds. That's because the bounds are also changed. So these are the bounds in terms of theta are pi over 3 and pi over 6. However, we are using u as our function. So the new bounds would be cosine of pi over 3 and cosine of pi over 6. We're plugging them into the u function. Right, so here's our u function. We're plugging the bounds in. So what we end up doing is, what is the integral from pi over 3, which is 1/2, and lower bound root 3 over 2, and this would be 1 over u du is maybe the more familiar way to write it, which is equal to negative natural log. We usually write in the absolute value of x because natural logs and any logs can't be a negative number, from root 3 over 2 to 2. When we plug that in, that becomes negative ln of 1/2 plus, simplifying the negative, ln of root 3 over 2, which you can leave like this, or you can also simplify. And when we have a negative and a positive with our logs, that's the same as writing it as a division problem. So root 3 over 2 over 1 over 2, sorry for that bad handwriting, which is equal to the ln of root 3 as our final answer. This can lastly be a really helpful problem when you end up with something like we see in number 3. Number 3 says, what is the integral of x over 1 minus 4x dx? Now, what I'm going to use here is I am going to say, well, this would be so much easier if the subtraction was on top, because, and this is just a nice quick review over to the side, if I have a plus b over x, I can separate that. That can be a over x plus b over x. That's great. However, if I have x over a plus b, that's as far as I can divide. I can't actually do anything else. So u-substitution can help us change where that subtraction is happening, and I'll show you how. I'm going to call u is 1 minus 4x. And I am going to then replace x as well up here. Using my solving skills, I will say u is then equal, u minus 1 is equal to negative 4x. So therefore x is equal to 1 minus u over 4. This is just using our basic algebra skills from earlier classes. And here du dx is equal to -4. So dx is equal to -1/4 du. So with our three different substitutions that we have here, we have a u, we have an x, and we have a dx. Our new integral is going to be 1 minus u over 4 all over root u times -1/4 du. And probably a lot of you are saying, Ms. Ross, this is not easier. But with a little bit of algebraic simplification, we can factor out the 1/4, and we end up with -1/16 as our coefficient, because we're factoring out this fourth here, and we're factoring out the -1/4 here. And then 1 minus u over root u du, which we can simplify further using these steps right here, where I am going to separate it into two separate smaller fractions. 1 over root u minus u over root u. So the actual thing that I will end up integrating is u to the -1/2 minus u to the +1/2 du. I'll leave that integration polynomial root work to you. If you're interested, the answer is on the guided notes PDF. If you have any questions about u-Substitution, I know I went through 3 radically different examples. Please don't hesitate to set up a Zoom meeting or leave me anything in the comments and nominate any problems that you're stuck on in the form on Google Classroom. I'll talk to you later.